Welcome back to Knowledge Hub. The uncertainty principle. Uncertainty principle, also called Heisenberg uncertainty principle or indeterminacy principle, statement, articulated, 1927, by the German physicist Werner Heisenberg, that the position and the velocity of an object cannot both be measured exactly, at the same time, even in theory. The very concepts of exact position and exact velocity together, in fact, have no meaning in nature. Ordinary experience provides no clue of this principle. It is easy to measure both the position and the velocity of, say, an automobile, because the uncertainties implied by this principle for ordinary objects are too small to be observed. The complete rule stipulates that the product of the uncertainties in position and velocity is equal to or greater than a tiny physical quantity, or constant, h, 4 pi, where h is Planck's constant, or about 6.6 times 10⁻34 joule-second. Only for the exceedingly small masses of atoms and subatomic particles does the product of the uncertainties become significant. Any attempt to measure precisely the velocity of a subatomic particle, such as an electron, will knock it about in an unpredictable way, so that a simultaneous measurement of its position has no validity. This result has nothing to do with inadequacies in the measuring instruments, the technique, or the observer. It arises out of the intimate connection in nature between particles and waves in the realm of subatomic dimensions. The uncertainty principle arises from the wave-particle duality. Every particle has a wave associated with it. Each particle actually exhibits wave-like behavior. The particle is most likely to be found in those places where the undulations of the wave are greatest, or most intense. The more intense the undulations of the associated wave become, however, the more ill-defined becomes the wavelength, which in turn determines the momentum of the particle. So a strictly localized wave has an indeterminate wavelength. Its associated particle, while having a definite position, has no certain velocity. A particle wave having a well-defined wavelength, on the other hand, is spread out. The associated particle, while having a rather precise velocity, may be almost anywhere. A quite accurate measurement of one observable involves a relatively large uncertainty in the measurement of the other. The uncertainty principle is alternatively expressed in terms of a particle's momentum and position. The momentum of a particle is equal to the product of its mass times its velocity. Thus, the product of the uncertainties in the momentum and the position of a particle equals h, 4 pi, or more. The principle applies to other related, conjugate, pairs of observables, such as energy and time. The product of the uncertainty in an energy measurement and the uncertainty in the time interval during which the measurement is made also equals h, 4 pi, or more. The same relation holds, for an unstable atom or nucleus, between the uncertainty in the quantity of energy radiated and the uncertainty in the lifetime of the unstable system as it makes a transition to a more stable state. Thanks for watching.